All right, virtual reality. That's the next one. I'm just going to give a little overview. I know that most of you have listened to some of the things I've said before, so most of you will have heard this. How many are just cold and really don't know what I'm about and haven't listened to a lot of my tapes or stuff? You know, just Keith in the back, he's the only one. Yeah. All right, so everybody's pretty well experienced. I won't have to do this very much, but I want to just get it fresh in your mind because it's going to, we're going to need these concepts in what I'm going to talk about later. Virtual reality, well, you all know, of course, that in my theory, this reality we call physical universe is a virtual reality. And virtual reality, you know, means it's a computed reality. You may also call that a simulation. Okay. Virtual realities have some basic fundamental concepts across the board. If it's a virtual reality, then it's like this. Okay. There's some of those things that are all virtual realities are like that. So that's why I use the World of Warcraft or the Sims as a model, because a lot of the way the Sims and World of Warcraft work, that's just how this reality works too, because the fundamentals are the same. Now there are differences too, but the fundamentals are the same. And I just want to mention the fundamentals. In a virtual reality, you have two characters really. One of them is a real character. We call that the player. Okay, in a computer game, the player is the one with the computer and the mouse or the keyboard that's operating. The other character, which we call the avatar, the elf in the World of Warcraft, the avatar, and you are the player. Okay, now, the virtual reality from the elf's point of view, or of course, if we're talking about us in this reality, it's from our point of view. All right, we're the elf in this virtual reality that we're all sitting in now and interacting here. So from the elf's view, and I use the elf and the World of Warcraft because when you think of it in your own terms, it's very confusing. If you think of it in terms of the elf, it's very easy and clear, you see, even though it's the same thing. And that's the difference is that here we have beliefs, and those beliefs run counter to concepts of virtual reality. And we can't help but have those beliefs. They're in our culture. It's just, it's in the, you know, we share that mindset with other people. It's the dominant mindset. So it's confusing to think about these concepts here, but the elf is easy. So in the elf's viewpoint, in his virtual reality, in his World of Warcraft map, there's a couple of things that are important. One, he is in a different reality, of course, than his player. To him, the player is non-physical. Right? The elf doesn't see the player. The player is not in the virtual reality. Also, the elf cannot see the computer. The computer has to be in a different reality than the elf. So that's a major concept right there. To the elf's viewpoint, the computer and the player are non-physical. That's because a virtual reality can't compute itself. So the computer that computes it can't be inside the virtual reality that it's computing. So that just doesn't make sense. It's illogical. So what does that mean to us? That means that our consciousness, and if we consider ourselves the body, then our consciousness is the player. We're the elf. Okay. It also means that the computer, or what is creating this virtual reality, also can't be in this physical universe. It has to be outside. It's non-physical. So the consciousness and the computer have to be non-physical to us, because that's just a characteristic of a virtual reality. Okay. So that's very fundamental to what we're going to talk about later. Next is that the computer and the player have to be in the same reality frame. And that's because they're communicating. They're sending data back and forth. You don't do that across reality frames. Reality frames are kind of self-contained. So there's a lot of communication between the player and the computer. And sure enough, in the World of Warcraft, we, the player, and the computer, which is some server, right, sitting in a building somewhere that serves up the World of Warcraft, we're in the same reality frame. And sure enough, in this game, it's just us and the computer. We, the consciousness, and the computer passing information back and forth. I tell the server, make my elf run away. And the server sends data in my data stream to my computer. Right? That's the data stream. I have my own data stream to that computer, sends in my data stream a picture of the elf running away. So then I look at that and I say, oh, tell my elf to run faster. So the computer does that and the elf runs as fast as he can. See? Now I may say, well, tell my elf to fly. And the computer won't do it because that's against the rule set. In this game, elves can't fly. So you can only do what the rules say. Okay, so this is the nature of a virtual reality. So who are you? Are you the avatar or are you the consciousness? Well, your body is the avatar. It's a virtual reality. It's a virtual body. Okay? A virtual camera, taking virtual pictures, virtual screen in a virtual building. So all of this, now we instinctively think this is all material. Well, it does seem that way to us, just like the World of Warcraft seems very material to the elf. But we the decision maker, we the choosers of what to do, we who decided to come here and now who are listening, we are the consciousness. We're not the body. Okay. So, other thing I want to mention here is that we see that this trade of information between us as consciousness and the computer is individual, right? Everybody playing the World of Warcraft has their own individual data stream. And everybody playing the World of Warcraft is really playing their own game. And that game is different the way everybody sees it. We're like that. So we all have our own data stream, personal data stream. We all live in our own personal reality. Now the reality is shared. We kind of all know we're here in this room. We all see something similar. But what that means to us and how we actually see it is all individual. Because everybody takes in the data and has to interpret it according to their own history, their own background, their own understanding, their own experience. So everybody lives in their own personal reality frame. And within that frame, you make choices. Now we said that the elf couldn't fly. That's because there's a rule set. And there's two constraints that are both in the World of Warcraft and here. One is that you can't do things that aren't supported by the rule set. The second thing is you can't do things that aren't consistent with what you've done before. So if you're the elf and you happen to be, you walk into a building, and when you walk back out of that building, you're going to be the same place you were before you walked into it. You're not going to walk out of the building, in some other part of the map, because that would be not a continuous history. Now you'd be teleporting someplace. Now, if teleporting is in the rule set, well, maybe you can do that. But teleporting is not in our rule set. So you have to have this historical continuity is one, and you have to abide by the rule set. Those are the big constraints. All right, now the last thing is that the virtual reality is probabilistic. I'll try to tell you a little bit about what that means because we're going to kind of delve in a little bit more about probability and why and how it's probable and how it's computed. It's a probabilistic reality like this one is really a combination of probability and deterministic kinds of computing. Okay. So what you have in the beginning is a rule set. That rule set just defines how things interact. Energy exchanges, connections between things. That's what it defines. That's pretty deterministic. That's algorithmic. Okay, so that just happens that way because that's the way the rule set says it happens. So that's kind of like your normal computer model. Okay, that just describes the rule set. But besides that, there are two other things that have to be included. One is that a lot of natural processes have randomness in it. Okay, if you have an unstable element, the way it decays, what particular atom is going to decay and go from, this state to a different state and then send out a particle in that decay, nobody knows. You can't look at it and say, okay, this atom's next. The next atom that goes in this decay process is going to this one right here in the corner. You can't say that. It's a random process. It just happens. You can't even say when it's going to happen. It happens whenever it happens, and it happens to, one or two of those atoms. And yes, you can measure that there's a certain rate of decay. Particles come off fast or they come off slow, which means you have a half-life that's shorter or longer. But as far as what particle decides to, change state, it's just random. So there's a lot of things that are natural in our reality that are random like that. Our own biology is pretty random. How all those chromosomes go together, how the DNA from the two people ends up in one child. There's a lot of just randomness of how that happens to go together. There's billions and billions of combinations, but only one of them out of all those billions and billions is the one that's actualized. So there's a lot of randomness. So when you add randomness to the deterministic part, to the rule set, you automatically get a probabilistic model, because a deterministic model can't have randomness in it. If it has randomness, it's not deterministic. Deterministic says there is only one path it can take, and this is it. That's determinism. And there's almost no computer models of any consequence that are deterministic, because we don't have the computer power or the know-how to start at the very bottom level and deterministically work our way up. We'd have to start with elementary particles, put those together to find atoms, put atoms together to make molecules, molecules together to make physical things, and then let the physical things interact. That would be a deterministic model. But we just look at those lower things, the elementary particles, the atoms, the molecules, and we say, well, that'll just take care of itself. That's a process that's beneath what we're looking at here. So we just assume all that works. And if we have to get into that, we do it statistically. Like with radiation, if we were going to look at radioactive plutonium or something, we'd model that with a random number generator that would decide when particles get tossed out, because we can't do it deterministically. Same with the genetics. You couldn't do that deterministically. So besides that, if you have a model like the World of Warcraft doesn't do it this way, but well, it does actually. It does a lot this way. If you have a model that gets complicated, it takes a lot of computer time to start at the bottom and work your way up to the top in any calculation. To start with the small stuff and work your way up to the action. Very intensive processing. So what people do when they make these simulations of complex things is they use the deterministic part to generate statistics of how things generally work. Okay, so if you don't have enough computer speed, then you take a complex problem and you run just that piece of the problem, and you run it 1,000 times, and you do all the variations that you can, and you see how all those thousands of times run out, and now you make a probabilistic model of that from that data, and then you put that in place of that real complicated thing. Now a probabilistic piece is easy. See, when it's probabilistic, all you do is when that thing we're talking about that we modeled over months in detail, we run 1,000 times, use that data to make a probability model of that same thing. Now, when that thing has to, you give it its input and you want to know what its output is, you just reach into your probability distribution, take a random draw from it, and that's your output. You see, that takes a couple of nanoseconds in a computer, whereas calculating that every time is very inefficient. So that's why complex models tend to be probability models, because there's a lot of complex stuff going on here. If the computer had to start with molecules and work its way up to me waving my hand in the air, that would be a tremendous process. So it doesn't do that. It's too much calculation. So that's why we have a probability model. So all of these processes that we do and experiments that we do, the system can do in terms of probability. So I build a machine. And when I build that machine to do a function, let's say it's a computer. I make a computer, or I make a, well, we're going to talk about an experiment. I do the double slit experiment. And I've got the laser, and I've got the slits, and I've got all this stuff. Okay, that's sort of a machine. I can reduce that whole machine to just 3 draws from 3 different probability distributions. So now instead of calculating the laser and the gas that gets pumped up and the atoms that collapse and the radiation that comes out and how it gets focused and all of that stuff, all I have to do is take 3 random draws, I'm done. I've got the solution. I know what's on the screen. You see, that's the way a probability model works. And that's the way our reality works. And then when we try to do the double slit, we get so confused because we don't understand how a particle could go through 2 slits at one time. See, there is no particle. There not only is no particle, there's not even any probability wave. It's also just made up. It's just 3 random draws, and here's the answer on the screen. You just look at the logic of the problem and turn it into probability. So we're going to see how that works. Okay, I'm going to talk just a little bit about action at a distance. Action at a distance is an easy thing or a natural thing in a virtual simulation, right? Because in the computer, you can always have a if-then statement. If this happens, then that happens. And I can say, if this happens over here, that'll happen over there. It's a computer program, not a problem at all, right? And you can make a simulation that when this thing happens in this part of space, that thing will happen in some other part of space. Easy to do. In a physical reality, it's a big problem. What is this action at a distance in a physical reality? How does that work? And we have a lot of action at a distance things going on here, like magnetism. I have a magnet here, and this is the North Pole, and I have one over here, and that's the South Pole. Well, what happens? They pull together. How do they do that? There's no connection. There's nothing there. A big gust of air doesn't push them or anything. We don't see anything. We can't measure anything. We can't find anything. All we know is that happens. I have a charge here, and I have another charge here, and if they're both negative, they repel. Just a problem there. And if they're different, they attract. Okay, that's the way it works. Again, there's no physical process going on there. And when physicists look at action at a distance, it makes them very uncomfortable because there is no physical process. But there it is, you see. So I'm going to tell a little story, kind of make something up, because again, I'm going to put it in terms of the elf in his virtual reality because it makes it easy for us to see the point. And then I'm going to take the point and I'm going to move it back over to our reality, and it'll make us easier then to see it here. It has to do with action at a distance. We're going to assume that there's a virtual reality. It's not World of Warcraft, some other virtual reality, but it has an elf in it. I guess just because I like elves, and that's a good thing to say, because if you say elf, then nobody confuses it with this reality. So in this virtual reality, we have a rule set, and the rule set allows this kind of action at a distance. And that is that if the elf waves his a little wand, like a music conductor, they hear music. Music comes from over here. And that's just the way this rule set works. So in this reality, you can pick up your wand and you can orchestrate and make music. Okay, and of course, that's a big mystery in this reality because the elves don't know how that works because it's action at a distance. There's no connection. You do this and something happens over there. Okay, so that's a problem for the elf scientists. But you know, they come up with things like, you know, the angels make the music, right? They make up things like that. That's like a long time ago we said the angels push the sun and the moon and all the stars around. That's why they move across the sky. The angels push them. Well, here they said the angels made the music. Well, there was this one scientist elf, and he really got annoyed with this idea the angels make the music. He says, that's just nonsense. So he took a lot of data, all the motions that you could make, and all the sounds that would respond to that motion. And he studied it, and he worked on it, and eventually he came up with a mathematical model that could predict what motion would produce what sound. So he could say, okay, if you move your wand like this, you're going to get that kind of sound. And to prove that it worked, he had that wand move in a way that nobody had ever done before, something, you know, really crazy, and he predicted the sound. And sure enough, that's the sound that they got. So now we have a model, a mathematical model that is emulating the rule set, right? He's in a virtual reality. The virtual reality has a rule set, an if-then statement, and the elves just figured out what that rule set is, how that works. Okay, because just there's an if-then, that then can be complicated. It doesn't have to just be a simple then. You know, if I raise my hand, a foghorn sounds. It's, you know, it can be a lot more complicated than that. So the then can be a bunch of mathematics, a bunch of rules. So now we have a scientist elf who has figured out how the rule set works in this action at a distance. And people, though, say, but okay, you figured out how to predict the sound that comes from motion, but where does the sound come from? Well, the elf can't answer that question. All he's done is predict what the sound will be given a motion. He understands the rule set, but he can't answer that. Where does the sound come from? And that's a problem because people start saying, oh, it comes from the angels. He really doesn't like that. Okay, so he tries to say, well, the sound comes from the math, right? I've got this math, and it goes from here to here, and it's the math that makes the sound. And of course, everybody laughs, and nobody believes him because that doesn't make any sense at all, right? But the math makes the sound. So then he looks at the math. He says, well, you know, I'm just going to make an interpretation that what this math is, it represents a force field. There's this force field. See, the math tells you how the force field works. And this force field, when I do this, it creates a force field that then goes over here and moves the air around in such a way that it makes a sound. All right? So I figured out where the sound comes from. It's this force field. But you see, there is no force field. That's just a trick. The sound is, I mean, what he's saying logically is that the math makes the sound. We're right back to that thing that's obviously silly, but he's just changed the way he's talking about it. Instead of saying, the math makes the music, and everybody laughs at him, he says, the force field, which is this math, represents that, makes the music. And everybody goes, oh, wow, he finally figured it out. You see? Okay. All he's doing is predicting a result, an effect, from a stimulus. Right? That's all he's doing, and his force field just does that. It makes a prediction, but it doesn't actually cause the music. All right, so that's easy. We see that with the elf, right? Obviously, the math doesn't make the music. And we know what makes the music. It's the rule set. It's the virtual reality. right, makes the music, because that's part of the rule set. All right, now let's go back to physics. We in physics have these action at a distance problems, and they come up in many ways, and we have done exactly the same thing. And what are our force fields? Well, one of them is called an electric field. And then there's magnetic fields, and there's electromagnetic fields. There's all sorts of fields. There's gravitational fields. Right? All these fields is the math that can predict the result gets turned into a force field that causes the result. So they all go back to the logic of the math makes the music, or the math moves the charge, or the math pulls the magnets together, which we know is kind of silly. But the force field does it, we believe it. So there is no such thing as an electric field. An electric field is force per unit charge. Okay, so you have two charges, and force is real. You can feel those charges repelling or pulling together. The force is real, and the charges are real. But force per unit charge is just an abstract mathematical concept. It doesn't exist. So, but now I'm talking over this mic, this lavalier, and an electromagnetic field is going to that receiver. Right? Action at a distance here. You guys use your computers, you go into your LAN, right, or your WAN, you hook it up, you get a signal, you suppose your cell phone, you talk, and when you talk, somebody somewhere else hears you. And why is that? Electric fields, electromagnetic fields, radiation, and picks up, this is a physical, this microphone I have here is a little diaphragm that vibrates when the air from my voice vibrates it. And it's got a little diaphragm with some carbon particles behind it. And as the diaphragm vibrates with the air vibrations of my voice, these carbon particles get smushed or pulled apart. That changes their resistivity. That makes a little electrical signal that varies just like my voice. Okay, so all that's physical. And then it gets transmitted to a receiver over there, sitting on a table. That we need an electromagnetic field to do that. Now that antenna over there has little electrons in it, and they move up and down, same way they move up and down here on the transmitter. So it's an action at a distance, and that's what that transmitter picks up and sends to that microphone, to the recorder over there. Everyday stuff. So here I am, physicist, telling you electromagnetic fields don't exist, and I'm using them to transmit my voice over that phone. You see, it's action at a distance. It's the rule set. It's just action at a distance. Why does that work? Because the rule set is set up so that works. If I do this here, that happens over there. And our electromagnetic fields are simply calculations of, if I do this, what will happen over there? That's different than you're just predicting an event, predicting a measurement, what's going to happen. And we can do that. We look at we can get a charge, and I say, here I have a charge, a positive charge. And if I put a negative charge over here, what's the force going to be? We can compute that. It's going to be a force in this direction, with a certain strength because of the size of these charges. So we can compute that. But then we say, why does this move? Well, it's because there's this electric field between them, and we used to call that the lines of force, right, in the field. And it's a force field, and you'll let this charge go, and it'll move this way if you hold this one fixed. It'll follow that force field. That's why it moves. See what we've done? We've made a prediction, but now we've created this concept that actually turns out to the math makes it move. Why does this charge move from here? Well, it's the math that makes it move. Well, that's silly, but it's the field that makes it move. Very the same thing. So that's a new way of looking at the world. So we think of action as a distance as almost magic. right? And we need these fields to convince us that they are real, because we, technical people, don't like angels making music. We don't like things that are magic. We want things to be physical. Now, when these force fields first got introduced in physics, there were a lot of physicists that grumbled about them and did not like it. They knew that it was not the math that makes the charge move. Okay, and they said, that's not quite right. But since they didn't have anything better to say, and since saying it's magic, wasn't very technical, I have no idea, really wasn't very acceptable either, then the force fields became in regular use, and we understand them, and they're so much part of our culture that we have come to believe in them as real things. Now, they have other effects too, because this radiation, if you get too much of it, it'll damage your body, right? If you get too much radiation, if you're around, things that radiate energy, RF energy or anything else, you stand too close to a big radar or whatever, it'll affect your biology, cause cancer, does these other things. Well, that's just another effect. It's another effect at a distance. There's something here, it causes effects. It can damage your body, it can duplicate itself in an antenna, it can do all sorts of things. It's just action at a distance. So when you understand that, then you realize that what it's telling us is that this is indeed a virtual reality. Action at a distance. How else can you explain action at a distance other than it's magic, than saying it's computed, because that's so easy to do when you compute a reality. So we have lots of these action at a distance things going on. So electric and magnetic fields are simply mathematical models that help us predict effects of real forces that cause real effects at a distance. Okay, we measure the effects, then make up math models that work as if a force field existed. But the emphasis on as if a force field existed. Or particles. We do the same with particles. See, these days everything's based on particles. They've even given up. The force fields have been replaced by particles. So we don't talk so much about fields anymore as we used to. Now, all the forces are an exchange of particles. Well, it's not so much that there's a force field there, it's that there are photons being exchanged back and forth. And we can explain all the nuclear forces, all the forces in physics now are explained by exchanges of particles. It's the same thing. Those particles are not really real particles. If you ever treat them as a real particle, and you don't get the right answers. You can only treat them in terms of probability to get the right answers. So they're not really particles, they're kind of quasi-particles. And where do they come from? They came from the math. So it's, again, the math does it. All these forces, the math does it. Gravitation works the same way. If you have, it used to be, and back in Newton's time and for a long time until Einstein came along, the reason we have gravity is matter attracts each other. All mass attracts other mass. Unlike charge, there isn't any negative matter, all matter just attracts. Okay, so the reason that the moon goes around us is because it's attracted and it has its velocity, so it just goes around in a circle. All masses attract each other. Now, we're looking for that force field that does that. There's no force field. There's only a gravitational field, of course, that's our force field, gravitational field. It's just a mathematical construct. It doesn't really exist. And now, because you could say, why? Why do masses attract each other? See, why, where does the music come from? It's the same thing. Why do these masses attract each other? Well, they do. And that's about it. It's gravity. It's the gravitational field is why they do that. See the point? There is no reason why masses should attract each other.
You just do because it's part of the rule set. It's action at a distance. So for the physicists out there, I'm probably going to take out a contract on me after I said this. I've just stomped all over, you know, this is heresy, but it's a simple thing. When you look at it, you realize that what we've done is we've taken the mathematics and confused it with reality. We've started to believe our own story. We didn't believe it in the beginning, and a lot of people, you know, fussed about it, but then eventually time goes on. It's just a convenient way to deal with things. And it lets us develop technology. Because of these electromagnetic waves, we can make these kinds of gadgets and gizmos, because we can compute what's going to happen over here when I do this. So I can use that to build stuff, to make technologies with it. And that's terrific. So it's handy to know what the force per unit charge is, because now I can calculate what that force is going to be anywhere in space over here. So it's nice, but it's just a mathematical calculation of an understanding of the rule set. You could just as easily say, there's no field. It's just the way our world works, is that if you put something in space, you have a charge here. Well, every other point in space in the whole universe will have some reaction. If you put another charge there, there'll be an attraction between them. The further away it gets, the less the attraction will be. It goes as the product of the two charges divided by the square of the distance. That's what it's proportional to. So if you go twice as far away, it's 1/4 as strong. That's the way the rule set works. Okay, so then we can say, well, space has this information. If I've got a charge here, this piece of space over here has information of what the force would be if I put a thing over there. Now we've gotten rid of the field and we're just saying space contains the information. And I've seen calculations where physicists have come up with how much information is there in a unit of space. They do that calculation and they say, well, you know, there's a lot of charges, there's this, there's that, there's gravity, there's all these things that are action at a distance. So space has to have a lot of information in it. And they calculate how much, and then they multiply that by how many units of space there are, and they come up with this huge number for the amount of information that's stored in space. It's all nonsense. Information isn't stored in space. Space isn't a little chunk of memory. It has values in it just in case somebody wants to know, you know, what the charge would be or what the force would be if I put a charge over here. That all gets calculated on the fly when it happens. I put a charge here. Now, if I measure over here, I'll get a value, a force over here. If I don't measure anywhere else, I calculate it anywhere else. So that's a waste of time. So it's not like space holds all the information. It doesn't. It's because I make the measurement that I get the information from my data stream, from the rule set. So it's only when the measurement's made do we get the information. The idea that information or space holds information somehow makes the problem very complicated, huge, and so on. You get a calculation when you make the measurement. You don't make a measurement, no point in calculating, you know, what that space, what the force would be if I put a charge in that space while I have one over here. I mean, why bother calculate all that unless you need it? So you only calculate when the measurement's made. Now these are a bunch of obvious things I'm telling you, but we're going to move on a little later to the double slit experiment, and you'll see that all of this kind of comes together to give you a whole different picture of how that works. Okay. So that's in the physics world, what we say is that we are interpreting the physical application, I guess, of the mathematics. So we say, yeah, we know mathematics doesn't cause things, but we'll interpret it for this physical cause. And then we forget that our interpretation is just an abstract interpretation. We start believing that that's the way it works. We start believing the causality of it rather than it's just an interpretation, and there is nothing real about it. So you see, you live in what seems to be a very magical world. All sorts of things that just happen with no reason. Charges, magnetism, gravity. Any of the action at a distance stuff is like that. And we can make up fields or we can make up particles. Actually, we replaced fields with particles to a large extent now. So it's all these little quasi-particles that run back and forth. It's just another way of doing the math. You see, problems will have multiple solutions in math. I can solve a problem this way or that way. I can say the masses attract. That's what Newton said. Einstein said that masses deform space. Einstein didn't say masses attract. He says masses attract. That's silly. Why would masses attract? Look, they deform space. Well, why would they deform space? You see, it's the same question. It's just another mathematical model to get to the same answer. Well, I can have a force field, or I can exchange particles. It's another way of calculating what this effect over here is from this stimulus here. And then we believe it. We think it's real. We think all these particles are real and they're all exchanging, but it's just math. Another thing you'll hear, of course, is that Mother Nature must be really good at math. You probably heard that. Mother Nature is really good at math because all the things we see are so mathematical. We look at seashells, and the seashells will curve in this precise mathematical series. You see, everything, how is it that physics is so good at emulating this reality with mathematics? How come when we figure out the rule set, it's not a set of philosophical statements, it's mathematics? See? Okay, we can emulate this rule set. We figured out a lot of the rule set in physics. And it's all in mathematics. So Mother Nature speaks math. Why is that? And I've heard that question as a deep, fundamental question asked many times. It's just an amazing thing that it should be that way. Well, if this is a calculated reality, a virtual reality, calculated from a rule set, what other language could Mother Nature speak? It's just a simulation, right? It's math. It's a rule set. Rules are logic. Math is just symbolic logic. It's the logic of quantity. That's what mathematics is. We have quantities. Everything can be measured in terms of its quantity. Size, shape, density, whatever. These are all quantities. Speed, all quantities. Mathematics is the logic of quantity, how the quantities relate to each other. So that's kind of hopefully an eye-opener for some. To realize we do kind of live in a magical world, but that magic is called the rule set. And the idea that this is a virtual reality sounds more and more plausible. The more you see, the kind of the misunderstandings that we all operate under. We kind of make it into a physical reality with our imagination and our beliefs. But in reality, every way you slice it and dice it and look at it, it comes out. It's got to be a virtual reality because that's the only thing that actually explains the data without some sort of trick.